Merci Jean-Paul. Bonjour à tous. Welcome everybody. It's a great pleasure for me to introduce the next speaker, next presentation from Professor Nakamura. You've been assistant professor at the University of Tokyo from 82 to 87. Just checking if I don't say wrong things. And then you moved to the University of California, Santa Barbara, where you stayed 4 years, from 1987 to 91. And since 91, you come back to the University of Tokyo, where you are currently a professor at the Department of Mechanoinformatics. And your current research domain is on humanoids robotics, cognitive robotics, and all things related with neuromusculoskeletal systems, human modeling. And you will give a presentation, which is right here. And you probably will speak about humanoids robotics. Am I right? Thank you.
Okay, well, thank you very much, Professor Philip Bido and the organizer, Professor Jean-Paul Laumond. And I'm really happy to be here. And I had a chance to make a series of lectures 2.5 years ago in this conference room, and I'm happy to be back again. And the, my talk today is titled Robotics, Technology, and Human Science. Title is big, but I'm trying to focus on our current research on what we call humanoid robotics. Well, the Inoue Sensei said it's not the main influence, but this cartoon started 3 years or 2 years before I was born and continued up to when I was the second year of junior high. So it was really influential for our generation. And the, so what it meant is that it's not only a humanoid robot, but the cartoon included all the bright side of the science and the future. And it had a lot of message on space age, computer, atomic energy, and the bright 21st century. And much later on, the Tokyo Electric Company used this cartoon at their advertisement of the nuclear power plant. And as you know, the things has been very changed. Last year, the big earthquake hit the east part of Japan, and after the tsunami caused by the earthquake, the nuclear power plant in Fukushima had severely damaged. And within the 11 or 12 hours, the immediate action should have been made by the human operator, but it was really hard. So as Professor Inoue said, it was really hard time for robotic researchers in Japan that we didn't have the appropriate robot for that kind of situation. Well, after about a month later, I have talked to our colleagues in robotics community in Japan. We get together and discuss what to do and how to get the collaboration, not only in Japan, but also with the help of the colleagues outside Japan. And we are trying to organize and set up the system or task technical committee in the robotics worldwide team. But it has been a hard time, but I'd like to continue the effort with our colleagues and try to establish some important network among, not only among robotics, but also within the related researchers in the related field. Well, the things what is happening in Fukushima is very hard. The pressure contaminant vessel is severely damaged, and there are very narrow space that only the small machine or human can just go physically. However, there are a lot of the contamination, and it's very difficult point. And also, there are a lot of the water leakage. So the coolant or water has to be supplied not continuously, but most of them are leaking. So it's very hard to fix the leaking and keep the dynamic stabilization. So knowing that situation, as you know, Sensei again explained, the DARPA has announced a very challenging program featuring the robot. It doesn't say specifically humanoid, but robot that can do something human should do. And this challenge is very important for robotics community and humanoid robotics community, because in the long term, the humanoid is considered as the real work platform for this kind of the socially important problems. In Japan currently, the technology being developed for Fukushima power plant is basically considering what to be done now, but not considering what to be done in 10 years or 20 years. So I think this kind of effort can be done probably from the academia or probably from the collaboration within the international framework. Well, experiencing the severe damage or severe situations, I found that the meaning of robotics to me has changed. And this is the Pasteur quadrant that I learned yesterday. And it's a nice figure, and I'm really happy that robotics has wide spectrum from the bottom of this yellow layer to the top. But I think even the top, there should be the time constraint. So youth-inspired basic research has some idea on possible applications. So I think if it is really applicable, I think we should care that the technology should come out within some reachable limit of time. So that kind of the reachability is something I was missing. So I think it's very important for us to find and define the time constraints so that we can complete or deliver some usable technology if it is usable. Okay, humanoid robotics to me is the very fundamental things, and the fundamental quest is that computers that understand human and machines that support human activities. Of course, from technical point of view, more recently we are looking at the huge data set on human motion, behavior, language, and other knowledge related to the humans. So how to handle, how to compute, how to manage this data is a key technology. Well, yesterday, Jean-Paul Laumond was saying, move to act, to make his talk short. So I like these things because this is very close to my definition or my quest on the understanding human and supporting human activities. Okay, so again, this is related to Inoue Sensei's talk today. When he was fighting with the committee members in the space program in the government, I was writing a proposal discussing with him for possible application of humanoid robot on the moon. It was almost 3 years ago. And this was unsuccessful proposal. I have many of them, but this is one of the unsuccessful proposal. But I seriously think that the humanoid on the moon is a very realistic and important challenge we could make, and maybe we should make even now. So these figures I drew with our student, what can be done on the moon with a humanoid robot. So there are two scenarios. First, the unmanned missions for exploration and building the moon base on the human scale. So it's like building the human house on the moon. So human-sized robot is most appropriate to do that. And then, well, in this situation, technically speaking, we need autonomy, localization, manipulation, mobility. These are the very common but cutting-edge robotics technology. So gathering these important cutting-edge technologies, we will be able to establish this. And here, again, the teleoperation is one considerable choice. And after building the base, of course, there will be the opportunity of, sorry, this is manned missions. So human will go there and do the necessary activities on the moon. So in that case, the humanoid robot worked there could help the humans in the same human space. So I think not only building the, and exploring unmanned missions, the humanoid can assist the manned mission afterwards. And in this case, of course, more important technical elements are the autonomy, localization, manipulation, mobility, and communication. The human-robot communication is most important. So the difference would be teleoperation and communication. And I'd like to say these two sounds different, but it's basically include a very important key technology in common. So the communication means I'm going to focus on this topic in the main part of my talk, but the communication means understanding the human behavior, human language, human intention, and then predict humans, the next action or next behavior, and think robot or computer should think about what could help him or her. So those kind of the closed loop computation must be done in communication. Well, teleoperation, this is opposite way. The human is controlling the robot at distance place, maybe from the Earth or maybe from the moon base or somewhere else, but there is a distance. So the communication latency or limited and uncertain communication bandwidth is there. So that means that it is very important to have right communication data stream between robot and human. Of course, the most standard telecommunication is sending all the information to the remote side, including vision and other haptics or many others. But this is very costly. So we can compress and we can send the key information to the remote side. And this is actually done by the very common technology like the segmentation or grouping or semiotics, those kind of technologies. So from technical point of view, for teleoperation, I think the same human understanding technology is a key technology for this. Okay, so there is, of course, the Mars rover or other rover type, the robot system that explore the outer space. But of course, the exploration is the human exploration. So we want to, scientists or maybe people want to experience and see what the space like and what is being observed there. So I think not only just sending the analytic device, we should be there. Of course, physically being there is more important, more difficult. So the humanoid robot could be there, and we can communicate in the same size of, how can I say, the consistent information. So we can experience, having humanoid there, we can experience what the same size of a human-shaped robot can feel there. Okay, so this is the related, my fundamental quest. So we have worked on these topics since 1998, being funded by JST and maybe afterwards from JSPS and Monbu Kagakusho. And we have some publications. I'm just listed most related topics I'm going to cover. Okay, one of the founders of the artificial intelligence said in his book, Semantic Information Processing, that the key quest is how can one make machines understanding things. Of course, this is it. And I would say for me, or maybe for humanoid robotics, the key quest is how can one make machines understand humans? Okay, so do we really understand only humans? Actually, I found this this morning just near this Collège de France place. But when I was a kid, the face of cars surprised me, and it's like the human face to me. And also, this is not human, but we consider or we interpret their motion, intention by taking them as a human-like thing. Well, this is more abstract. This is not human, and this is not realistic animal, but we still, or maybe children still understand. This is very funny things. We tend to understand everything as we understand humans. So to me, I think reading many books on neuroscience or many cognitive science or other textbooks, the human brain spends a lot of resources just to understand humans. So I think we naturally use this kind of the functionality. So when we studied this kind of the development, of course, someone said that the small mammals, when it was in the Ice Age, having a hard time. They have to help each other, and they develop understanding each other. Of course, it was same for the ancestors of human beings. And we now have the big part of brain to understand the human. And I just named that functionality as anthropomorphic biological equipment. We have such equipment in the brain. So what if we have a computer to understand humans? So I think we naturally have this kind of interfacing functions. So what we need to do is a machine having comparative the functionality, what I could call anthropomorphic artificial equipment. So as we understand the human, if robot or computer could understand us, the communication becomes much easier. Very simple, intuitive. We don't have to look at the manual or learning the language or others. So this is very important part. We naturally have the system to understand human shape, human behavior. So if a robot can understand us, and also if robot can represent their motion in such a way we do, then natural communication start between machine and the human. All right, so what we need to do is to develop the anthropomorphic artificial equipment. And we'd like to see the human-shaped machine that is humanoid. Well, now, of course, the large computational resource like the cloud computing and the communication through wireless internet network is promising. So that this kind of communication could be supported by the large data set of humans. Okay, the system of symbols, when we were starting the first JST project, we were so fascinated by the articles about the mirror neurons. And mirror neurons is very controversial, and many people say, yes, there is many mirror neurons, and some other people say there is no mirror neurons. So it's still very controversial, but what it means that in the monkey brain, people found that the same neural portion activated when the monkey see humans' motions. And similar activation was also observed when monkey himself does the same motions. So it is very interesting. The one part of the neurons act at the perception and action in both directions. So, and another controversial thing is that the place where the mirror neuron was originally found was very close to what is called the Broca's motor speech center in the human brain. So being inspired, so we wanted to have single computational mechanism that can be used for perception and also actions. So we decided to use the mathematical tool like hidden Markov model, stochastic modeling. And stochastic system has well equipped by mathematics and algorithms. So it's very convenient. Well, this is the some equations of hidden Markov model, but it's not too important, just I would like to show. So with hidden Markov model, I just represented by this box. HMM is a hidden Markov model. And this is a model of particular sequence of motion, one sequence of motion. And having this model, we have some set of parameters. And using these stochastic parameters, we can, by observation, looking at the human motion, we can tell the probability that this motion is same as the motion that HMM remembers. So it can tell the probability. On the other way around, using these probabilistic parameters, we can generate within the probability the similar motion that is remembered by these parameters. So this hidden Markov model or set of parameters can be computed for perception and also for generation of the motions. So we introduced this mirror neuron model for the communication purposes. So we decided to develop some simple model of the theory of communications. And this is the idea. So this robot has a set of hidden Markov model. Let's say this is the set of hidden. This is a set of hidden Markov model. And maybe robot learned hidden Markov model for his perception and motion. But he can use same set of hidden Markov model to understand the human just next to him. And the result of understanding is going up. Of course, he knows his own motions. And then in the second layer of hidden Markov model, we model the relationship with two people, I mean, two parties. So then the relationship is perceived. And then we can send what kind of relationship to be made. So this is the highly intellectual part to be developed. But for the very casual case, we can just shortcut like this. In this way, if the relationship of the two are good, let's keep the good relationship. If relationship is not good, then keep the similar relationship. So this is very casual, and it's not very friendly way, but by defining some simple or complex model here, we can design the communication model based on the knowledge of perception and action for the robot himself. Well, this is what we showed the demonstration at Aichi Expo. And this is one of the projects that the Inoue Sensei introduced and accepted from 300 applications. So in this demonstration, what we are doing is a real-time fighting between humanoid robot and human. This humanoid robot is just 60 centimeters tall, and human is my student. So they are fighting each other with maybe 3 or 5 meters at the distance. And the student motion is captured by motion capturing system and interpreted by the Hidde-Markov model, and the robot motion is generated by the communication system I just explained. And they are communicating by fighting each other. And I'm going to show some other stuff that we have been working on. And, okay. Well, sorry. So, crystal ball is one technology. Okay, this is the motion captured motion in our lab, and this is the real-time data. So he's now doing this exercise just in front of me. And we have developed the autonomous segmentation algorithms. So his motion is autonomously cut into some segment, typically 1.5 or 2 seconds. And that's cut past the segment is going to the right. And what you see here is his future motion. So 1 segment ahead of time, he will be doing this. And 2 segments ahead of time, he will be doing this. So having the knowledge of the motion, this computer system can predict his future motion in this way. So the segmented data is stored in this way and clusterized. Okay. Well, this is the same data, and this is the past data. This is the future motions. And all of these past data is gathered and makes these kind of tree structures. And tree structure has the similar structure in the same branch. I mean, similar motion in the same branch. And on this side, you saw the temporal sequence of the different of motions. Yeah. This is the temporal sequence of different segments. So having the human data, we can create this kind of the data set. So this is like the subway system in Tokyo, actually. I mean, that particular motion is one sequence of exercise. That means one line of the subway station or subway line. So knowing the current station, it's easy to predict the next station. So the technology is something like this. But gathering many motions and building this kind of complicated subway network, using this network, we may be able to predict the many other or many new motions from our known motion data. So this is what we want to do. And actually, my colleague, Professor Takano, tested with the CMU data set, including the 50,000, over 50,000 motion symbols, and created the over 100 dimension vectors, feature vectors. And the tree structure becomes very, very complex. And actually, this is just showing the 20% of them. If we show 100% of them, it's a big black ball. So anyway, for this kind of data set, we can classify or classify the data set, and we can use for predicting the human motions. And having tree structures, of course, as you know, it accelerates the retrieval of the data or association of data. Okay, one of our ex-PhD student, Professor Dong-hee Lee, now at the Technical University of Munich, worked on the physical human-robot interaction. This is the real-time robot-human mapping. And also the Christian Otto in the, Dr. Christian Otto in DLR, he was also working with us at the postdoc, and he developed the physical interactive control technologies. And what I have already explained in the tree structure or segmentation clustering, that is only the motion image. It does not comply with physical constraint. So what is necessary is taking account of real physical constraint for creating the motion. That is the reality of robotics. And the physical human-robot interaction, in addition to the recalling the subway stations, the robot system or computer have to modify the motion pattern so that it can really touch something or it can really synchronize with the human. So in this demonstration, the Dong-hee Lee is making the experiment of the physical human-robot interaction. Her motion data is interpreted by numbers like this. So here is a number 0, 4, 5, several. So this is what the computer system understood from her motions. Then the robot have to generate to touch her hand, but the timing is not known, and the point of touch is not known. So they must be done by the additional computation. This is a physical constraint that we need to consider. So now, association between motion and language. Well, we developed the data set and network of the human motions, and we used the stochastic modeling. And the same stochastic modeling is being used for the natural language processing. And the language or text word and the motion primitive, what we call, can be quite consistently connected with the same mathematical framework. So we want to connect the motion data and the text or language data and develop the association from motion to the language or language to the motion. So of course, we have two systems, the motion language model. We call this is the structure that we created by collecting the human motions. And of course, we have some stochastic model of the natural language data set that we create. So we connect this and this. And with what it does is motion language model does is that if the human behave in the motion capturing system, then all kind of the how can I say, keyword related to the motion is created with some probability. And then these keywords are sent to the natural language model. And then some words are associated from the language model. This is just a simple association from word to word. And then based on the probability of connectivity of the word, we can create the word sentences and pick up the the highest likely, the sentence with the highest likelihood. This is very casual way, but what is nice is that this can be computed in the reverse way. From the sentence, we can divide into the word, and we can create a motion from the word. Okay, so this is example. So this is the what is interpreted. So this is the our student motion, and the language for the language we use Japanese, but just for the convenience, we are writing the English sentences. And among three, the first one is the highest likelihood, and the second one is the second highest, and the third one is third highest. So not all of them are, of course, equally important. Probably the first one is more important. And first one may be still very low percentage. So the quality is not very good at this moment. But from the motion, we can interpret and create a sentence. Okay. This is the other way around. So from the sentence, we can create robot motion. So sentence can be arbitrary. If we can completely unknown sentence, of course, there is no meaning at all. But if we changing the subject or changing some word, it doesn't matter. It can just pick up most likely movement from the stochastic point of view. And of course, there's no physical constraint considered. So of course, after this, we have to take all kind of the dynamics and physical constraint, or maybe object constraint. Well, at University of Tokyo, our department purchased the 30 of the now, and we used for educational purposes. And at the press conference, we showed these demonstrations. So the four robots are behaving differently, but this is the highest likelihood motion, and this is the fourth highest likelihood motion. So maybe you can see the difference of motions by using the now humanoid robot. Well, of course, maybe I should skip. So this is the physical demonstration for the first time we created, and it's not very successful and not really satisfactory. But we realized the things that we have to develop and the problems and difficulties of things. So I just want to introduce for you. Is it moving? Yeah. Okay. This is a humanoid robot, and Kinect is on top of the head. And we are not using the motion capture system in this demonstration. Using the Kinect, the Professor Takano's motion is measured and shown as the skeletal motion. And his motion is interpreted by the sentences like this. So motion is too simple, and the quality of the sentence is not really good. Sometimes it's good, sometimes it's terrible, but sorry, it's hard to explain. A player walks and a student pulls a rope and the student steps, student runs, a player avoid, student bow, student jump down, student play, a student make phone call, student drinks. Okay, so again, the next demonstration is very trivial, but we taught the template of the now head, and we give the command to touch the head. So within this image, knowing the template, the computer system will search for the head and try to touch the head. But actually, the robot remembers this kind of motion, the touching the very high head like this. But now it's very low, and of course, this motion must be modified so that it can comply with this physical constraint. And of course, it should avoid the collision, self-collision and collision with the table. All of these are computed. It takes some time, but modified like this. So the thinking of the motion pattern, usually we have that kind of the system. When we think of some manipulation or action, probably we think of the motion pattern. Then having the visual image or other sensations, we modify it to really do the job. So I think this kind of combination is very important and critical. Okay, the understanding human sensation. This is another topic I want to cover. How many minutes? 5 minutes. Okay. So with the motion capture system, we have the 10 cameras, and maybe we use 35 markers attached on the body and 16 EMG wireless detectors and 3 of the 6-axis force plate on the floors. And some time ago, we developed the musculoskeletal model. All kind of mass property is attached with the bones, and the muscles are modeled by the wires. 10 minutes. Thank you. Muscles are modeled by the wires. And in the current model, we have 989 wires to model all the muscles. So like this, the simple muscle is modeled by the simple wire, and big muscle is modeled by multiple wires, and something like this. So from robotics point of view, it's very standard computation. Knowing the joint angle or joint velocity or joint acceleration, which are measured by the motion capture system, assuming that all the mass are attached to the bone, we can compute the joint torque. What kind of torque that the joint have to generate, that is computed. And then we want to compute the equivalent wire force. This is a difficult part because our motion of equation in this particular case, they had 321 equations, but the number of wire is over 500. So there's more variables than the number of equations. So it's a difficult problem to solve. And of course, we have constraint that the wire tension should be positive or 0, but never become negative. And I just want to show the 2 equations to explain the computation. So first, we compute the contact force on the ground. If we have the force plate, we don't need to do it. But even without force plate, we can compute the contact force by the dynamic equations. This is being done by this optimization. And then we have second optimization to find out the real wire tension. And in computing wire tension, having the EMG wireless detector is very important because the muscles could co-contract, or maybe just if you measure if you see the famous athlete, they tend to use the minimum effort of the muscles. So they avoid the co-contractions between the muscles. But for ordinary people like me, use a lot of co-contractions. So the co-contraction, with co-contraction or without co-contraction are not observed by the motion capturing system. So having some reference signal as the EMG detector, we can partially solve this problem. So for 16 muscles, typically, we use the EMG detector and compute the reference muscle tension using the well-known Hill model like this, and use this F star as the reference of the data. And this is the example of measurement. So he's the famous professional tap dancer in Japan, and he said he could touch the ground 16 times per second. So this contact timing, detection of contact timing and contact point was the hardest problem for us. But after a while, we computed and superimposed in this way. And this is another example. This is the famous professional drummer, and he is very skillful, and he never see the drum set. So he can control his eye direction at his will. And how he does this is that he perfectly controls his center of mass, and he doesn't, change the position of the center of mass. And he only activates the muscles when it is really necessary. And making the sound, he releases the muscles. And what is interesting is that it is physically natural, but we didn't realize before we measure. So look at the right arm muscle and the left leg. So when he uses the right arm, the left leg is also activated. So in this way, the force moment are balanced. And with this control, he could keep the COM, center of mass, at this point fixed. So this is another example of top athlete in Japan. C is the Hiromi Miyake. He's an Olympic athlete coming to London, and he's a Japanese champion. And C controlled the position of the barbell very precisely, repeatedly. And what is impressive is that all of those athletes try to avoid the co-contractions, and C avoid co-contraction totally. And what she does is when she lift up the barbell, it's precisely just above the ankle. And in this way, the stability is maintained automatically. So this kind of skillful action is observed. Well, we have another thing. This is what we call magic mirror. This is a real-time application with a simplified muscle model. About the 300 muscles are grouped up to 50 groups. And 50s are estimated in real time and superimposed in real time. There's some slight delay, but not very much. Okay. Finally, I'd like to talk about nerve. So we want to have the computational system to observe or to estimate the sensation. So we have developed some technique to develop the muscle activities. But how we can get into further depths of the neural system? This is our question. And it is, I mean, anatomically, it is known that the big bundle of nerves are coming out in between two spinal bones. And the efferent signal goes out and then split into two. So at each gap between two spinal bones, there are four bundles of the nerves going to the muscles. So they go to particular muscles connected. So of course, these wires are not just single wire. It's a bundle of nerves. But we consider them as the scalar signals, one signals, and model the network. Okay, so the command is coming out from the spinal nerve. By the way, spinal nerve means the nerves coming out between the spines. Spinal nerve doesn't mean the nerves inside the spine. So spinal nerves go to the muscles and coming back, I mean, sensing signal is coming back following the same track. And then inside the spine, there is the connectivity between the nerves. So this makes the reflex. There are many other types of reflex, but the particular motion reflex is included in this connectivity inside the spines. So we don't know what kind of connectivity are there. So what we did is very simple mathematical three-layered ergodic neural network. And we trained this model by using this kind of typical motion data. He's working with this sound from 100 steps per minute to 570 steps per minute. And there are some other motion data. So having these simple typical motion data, we trained the neural network. And of course, we don't know if the neural network obtained has any meaning. But we just tested. This is the test of what is called the knee jerk. When we hit the tendon just under the knee, the sensing signal goes up to the spinal nerve and then spread to the other part of the body. And it is simulated in this way. So this is not very, but we could see some similarity to what we know about the how can I say, reflex motions. So my colleague, Akihiko Murai, he was a student, and our colleague, the Katsu Yamanade, were now in the Disney Research Pittsburgh, and Dr. Murai has just came back to our university, but they continued their work in the Disney, and they developed some lower dimensional model. Okay. So this is a simulation of the land model. So there is no stabilization control. This is just controlled by the neural network obtained in the spine. And the white, slight white motion behind this is the motion pattern that's being used to train the neural network. So of course, he cannot continue this work, working forever, but it shows some possible motions in simulation. But this is very interesting. The same neural network can exhibit very interesting properties. So again, he's working with a neural network, then hit like this. Then by the dynamics and neural network, the foot goes up, lifted. the same situation, but at the end of the swing phase, he hit the foot. Then he doesn't lift up, he pressed down. So this kind of different motion is created by dynamics and neural network. Well, one of our students tried to develop the reflex model, including cutaneous reflex, but this is just a starting point, so I try to avoid the time to spend 1 minute. So we are trying to develop the other musculoskeletal model for other mammals. So this is just a geometric morphing between mice and humans. And the mice has more spinal bone than humans, so there are some missing bones like this. So by this morphing, we can morph the muscle network to the mice like this. Of course, this is projected muscle network of human. It's not really same as the mice muscle network, but we can start with this and create the other mammals, the muscle network. And with our colleagues at the Liliane Bioresource Center, we are looking at using the genetically controlled mice, which has some typical motion disease. And we did some preliminary capturing. This is capturing. This is not the false information. This color just shows the change of the length of muscles. So if we could measure the contact force, and if we could know the mass properties, we can estimate the muscle activities in a similar way. Okay, so of course, medicine looking at the using a lot of human data, and the insurance company also looking at using a lot of human data. And I think we are in the age that we are going to collect a lot of human data, even if that is some technical problem of the personal information or many, but it is true that the human data will help many other things. And I think this is a region of anthropology, or maybe some sort of microanthropology. And I think our machines or humanoid can understand the human based on these huge data set. The application could be automobile, consumer electronics, and many others. Okay. Thank you very much.